it really depends on the symmetry of the crystal structure, right? Whether these kind of things are possible. And so there's a phase transition which takes place at a temperature called the Curie temperature, which distinguishes between these symmetrical crystal orientations where you do have a permanent dipole moment and those where you don't. And so in the homework there'll be a problem involving barium titanate when it is below the Curie temperature, and so when it does have this permanent dipole moment, and you will do a calculation to see what that dipole moment per unit volume is, polarizability. And I think that's it. This was a kind of intense lecture. It's a lot of material. It can get very complicated. This is probably as much in the weeds as we're going to go, I think, in this course. But I hope it's helpful. And so,
thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
okay, lecture 106, liquid and solid dielectrics. So what I want to do is I want to imagine, I'll write it over here, a capacitor. I'll put, this is the positive plate of the capacitor. So you can see that there's going to be an electric field, which I'm going to call E sub F for free charge. So whether we've hooked this up to a battery to create a potential across these capacitor plates, or whether we just simply accumulated some positive charges here, causing negative charges on the opposite metal plate to collect, right? And in between the plates of this capacitor, I want to insert a material. And this will be a dielectric material. And that's going to cause a polarization inside the dielectric material. Remember, we think of this as being composed of atoms and molecules, right? And so the atoms in this dielectric material, right, because of this positive plate, the electrons will be more attracted to it, right? And so it's going to kind of distort it or polarize it a little bit. And I want to focus our attention on a small sphere somewhere in the center of this dielectric material, okay? And the reason why, so how big is this sphere that I'm considering? Well, it has to be big enough such that things outside, so molecules, or remember these will be polarized, right? So dipoles outside of this sphere will be far enough away such that we can consider kind of the average field throughout the material, what I would call a macroscopic field, okay? So if the sphere needs to be big enough such that things outside of the sphere we can consider as just part of this macroscopic field. Right, remember, if you get really close to a dipole, right, depending on where you sit, you're going to feel different components of its electric field. If you're sitting near the negative side of the dipole, you're going to feel a strong negative electric field, right? You get attraction towards that negative charge. If you're on the opposite side, you'll feel, if you're a positive charge anyways, a repulsion, right, from that positive charge. So it depends on where you are. So you want to be far enough away such that you can kind of ignore the individual dipole effects from everything outside the sphere. Okay? But it can't be too small either. We want the sphere to be big enough so that we have quite a few dipoles inside of our sphere. Okay? So if I were to blow this sphere up, for example, and look at it more closely, I wish I had a different colored pen. I'm going to circle the dipole in the center. Depending on the material, whether it's a liquid, right, or a solid, if it's a liquid, these dipoles are going to be kind of randomly arranged, because in liquids things kind of bounce around because things bump into each other a lot. In a solid, they'll be more rigidly fixed. But in either case, because of this electric field that's been applied, right, it's going to be, what is the electric field that this sphere is going to see? It'll be the electric field from the free charges minus the electric field from the polarization charge, right? I think we call this sigma sub free, whereas over here, this would we call sigma sub bound. That's the bound charge density and the free charge density. And so this sphere will be polarized, and therefore on the surface of this sphere, and remember it's an imaginary sphere, okay? It's just pretend for the purposes of calculation. On the surface of this will be polarized because of the dipoles, which are going to be trying to align with the external electric field inside of the sphere. And so what is this polarization? Well, this, in the homework, the last homework assignment, we had a problem that was very similar to this. In fact, it may have been exactly this, where you're asked to calculate what this electric field due to the polarization here looks like. And you should have gotten that it's going to be something like this. We'll call it E sub s for sphere equals minus P over 3 epsilon naught. This E sub f field, I can write this down, the free charge field, right, is going to be the free charge density divided by epsilon naught for this particular capacitor arrangement, right? This is for a parallel plate capacitor. We calculated that in a previous lecture. What about the bound charge field? That's going to be in the opposite direction, right? It's a minus, and that'll be sigma sub b for the bound charge density over epsilon naught, which is just equal to minus p over epsilon naught. So I can think of kind of the macroscopic field as being the free charge plus the bound charge field. I think I use lowercase b, which is going to be sigma sub f over epsilon naught minus p over epsilon naught plus p over epsilon naught. But what I'm really interested in is I want to know what the electric field for a dipole at the center of this sphere is going to feel. Okay? So I'm not going to include that dipole in any of the calculations, but I want to know the electric field that it feels. Okay? And it's just really the sum of all of these fields. So you've got this macroscopic field E, which is composed of the free charge density, the contributions from the free charge density and the bound charge density inside the material, plus the electric field due to the polarization in the sphere itself, so we call it E sub s, and plus, I'll just call it E prime. That's the dipoles. I guess I could call it E sub d. That's probably better. E sub d. That's the electric field due to the dipoles inside that sphere. Right? So after we add all these electric field contributions up, we can then finally add up the contribution from each of the dipoles inside of that sphere. Now, if it's a liquid, because, if it's at a kind of a normal temperature, not too cold, these dipoles will be kind of randomly arranged because they're always rotating around inside the fluid, right? So that would be if the electric field was not really, really strong that we applied to polarize the material, and if the temperature was not really, really cold, such that everything is starting to freeze out. So in most cases, though, that are going to be of interest to us, this E sub d component is going to go to 0. Okay? So for example, if it was a solid, and we were in, say, a cubic crystal lattice, where all of the molecules inside the material are arranged in kind of a cubic fashion, right? We haven't really talked about solid-state physics and crystal structure, but in solids, they can either be kind of randomly arranged, kind of an amorphous material that doesn't have any real structure to it, or it can be a crystalline structure where every atom or molecule inside the material appears in regular intervals. And in that case, there are certain crystal geometries where the contribution will average out to 0, okay? And that's the case in certain materials, in cubic symmetry, for example. Other ones, tetrahedral symmetry, it would cancel out and it would be 0. But we're not going to get into the details of that. That can get rather hairy. But yeah, for the cases that we're interested in, either because of the symmetry of the crystal or because of the random motions in a liquid, right? The dipole electric field contribution to this dipole at the center of the sphere will be 0, approximately. And so we can ignore that. So we really have just these two contributions. So I can write, the M, by the way, is for, we'll call it the molecular electric field. Okay, it's the electric field felt on this molecule, which is located right at the center of this sphere. Okay? And so we can rewrite this as E sub m is equal to E plus P over 3 epsilon naught. Did I write that result down yet? Yeah, I did. Right here. So this is what you calculated in the homework. It's not that tough an integral if you know how to set it up. It's also called the Lorenz field, I believe. Also, I wanted to note that I think in at least the last lecture, or maybe it was the lecture before last, I don't remember, the units in electricity and magnetism can be tricky. There's several standards. There's CGS, which stands for centimeters, grams, and seconds. There's SI, which is kind of the standard unit, the standard metric unit system. There's MKS, and the formulas that we use in electricity and magnetism can be different depending on which standard you use. And I think I may have used CGS in the last lecture inadvertently. This time I'll use the SI system. And so when I write down what the dipole moment is equal to in terms of a polarizability, it's just going to be equal to the polarizability times the field. In CGS, it would be epsilon naught times the polarizability times the electric field. So you get slightly different units for these different quantities. And it can be a real pain in the butt, to be honest with you, dealing with that. And if I threw someone off by using CGS last time, then I apologize. I'll try to stick to just SI units in this lecture. And I was careful to check all of the units that I got in my calculations to make sure that they were in the standard units. So that means this is the dipole moment in terms of the molecular polarizability. That's this constant here, right? And we did a nice calculation last time where we considered a very simple model, right, of an atom and got an expression for the polarizability of that atom in terms of like the spring constant that holds the atom together. But what I want to do now is I want to relate this to I think the term is polarizability. That's why I'm taken aback as to what we call, I think we call this the molecular polarizability. And then there's the general polarizability, which is really just a measure of the dipole moment per unit volume. And that's the way I like to think of it. And so big P is the dipole moment per unit volume, and it's number of dipoles per unit volume times the polarizability, or the dipole moment, okay? So this is a dipole moment in terms of the molecular polarizability, and this is the dipole moment per unit volume. Yeah, so this is going to be equal to N times alpha times the molecular field, and now we're going to replace the molecular field with this. And so this, by the way, this P in here is the dipole moment per unit volume. Okay, so I can solve for that because this is dipole moment per unit volume equals something in terms of the dipole moment per unit volume. So I can rewrite this P times 1 minus N alpha over 3 epsilon naught equals N alpha times E. Dividing through by this, I get N alpha E over 1 minus N alpha over 3 epsilon naught. And if you recall, we also had a way to relate the dielectric constant, right, to the dipole moment per unit volume. And we said that the dipole moment per unit volume, now this is in SI units, that'll be equal to epsilon naught times kappa minus 1 times E, where kappa is the dielectric constant, okay? So if we look at this expression for the dipole moment per unit volume and compare it with this expression for the dipole moment per unit volume, right, we see that we have that epsilon naught times kappa minus 1 should be equal to N alpha over 1 minus N alpha over 3 epsilon naught. And this is known as the Clausius-Mossotti relationship. There's an alternative form that you can write this in, and I ask in the homework that you do it. It's not that hard to do. It's just a bit of algebra, but you can manipulate this to say, did I write it down? I didn't, but I think I probably remember it. It's going to be something like, you're going to solve for alpha, and you'll get that alpha, the molecular polarizability, is equal to 3 epsilon naught over N times kappa minus 1 over kappa plus 2. That's another way to write it. And I'm going to ask you in the homework to show that that's the case. That's just a pretty straightforward algebra problem, and you can use this to get that. And this is the Clausius-Mossotti relationship. Another problem that I'll ask you to think about in the homework is to think about how this relates to what we found for the dielectric constant last time. So you want to solve for kappa, okay? And you'll have kappa is equal to, looks like it's going to be like epsilon naught plus this stuff times epsilon naught. And compare that with the result we got last time where we considered a gas, right? We had this model of a gas, and we got an expression for the dielectric constant in terms of the molecular polarization or polarizability. And I believe that we got that kappa, so I think what we got was that kappa was 1 plus N times alpha. And so I want you to, in the homework, show that in the limit that N alpha is small, that the Clausius-Mossotti relation reduces to this simple expression here. And that also is pretty straightforward. Okay, moving on. I want to think about nonpolar molecules for just a minute. So these are molecules where the center of positive charge and the center of negative charge overlap such that there is no dipole moment. Okay, a polar molecule would be one where there is a dipole moment. Okay, an example of that might be H2O, where the oxygen unequally shares the electrons of the hydrogen, and so you get a center of positive charge defined by the 2 hydrogen ions, and a center of negative charge defined by the center of the oxygen atom, essentially. And there's a difference in those 2 positions, and so you end up getting a dipole moment. Okay? I want to think about a molecule we'll have, of course, the nucleus at the center, right? And we'll assume that the center of positive charge is right there at the dead center of the nucleus. Also, for the when we're talking about this stuff, I'm going to consider that the nucleus is clamped or fixed in position, okay? So any motion that's going to take place is going to be the electrons, all right? Now, in the Bohr model of the atom, we think of electrons orbiting, like planets orbiting the sun. However, for the purposes of this kind, that's not right. Quantum mechanics tells us that there's a different picture of what the electrons are like. But in the orbital picture, if you think about it, like what's the time period of these orbits? It's like a femtosecond. That's like 10 to the minus 15 seconds. So on relatively long time scales, they kind of whiz around in lots of different positions, right? So a femtosecond is a really short period of time. And for the kind of things we're talking about here, in the experiments that we're talking about here, which take place on the order of microseconds to seconds, the electron has been in lots of different positions. And so we're going to kind of think of it as being uniformly distributed in the form of a sphere around this positive charge center, okay? And we're going to call the radius of this sphere, so if I were to draw a line from the center to the outside of this sphere, we'll call that the radius r naught. And we'll think of that as like the size of this atom, right? If I said, how big is this atom? This is what I would think of as kind of its size, okay? Now that's if there's no electric field around. If I apply an electric field, right, the positive charge centers will be accelerated in a different direction from the negative charge centers, and what we'll end up getting is an induced dipole moment in the molecule, okay? And in that case, I want to think of the negative charge center as being somewhat separated from the positive charge center, okay? I don't want to worry a whole lot about this like electron cloud getting distorted. We're going to assume that it doesn't distort, that it just simply shifts over. So if I were to think about this distance r naught here, that's not the best circle, but you get the idea, right? And this distance here, we're going to call it d. So this is the amount of separation that it's done. And since I'm going to consider that this sphere, that the charge is equally distributed uniformly throughout this sphere, I want to think about a little Gaussian surface which encloses this negative charge, because if I think about the forces acting on this molecule, remember I'm kind of clamping the nucleus, right? So it's like pulling the electron cloud to the left, let's say, if the field is in this direction. And so we're going to have a force of ZE. That's the total charge for the atom, right? So if I have Z is the atomic number, okay, and E is the charge of a single electron or a single proton, okay? So I have this charge times this molecular field that we're applying. That's going to be the force that we experience in this model of the atom or molecule that we're considering, okay? And that force will be pulling the cloud over, but it's going to be balanced out because there's going to be a restoring force that is provided by the attraction of the electron cloud back to the nucleus again, okay? And I need to get a value for that restoring force. We'll use, of course, Coulomb's law for that, but I need to write something for the charge. So we know we're going to have ZE, that's the charge of the nucleus, but we also need something for the charge of the electron cloud, which we'll put here, and we'll then divide that by 4 pi epsilon naught times this distance d squared, because that's the separation, right? And so if we think of this charge as being uniformly distributed throughout this sphere of radius d, then we can see that the charge inside, ZE times x cubed, that's the volume of that sphere, divided by r cubed. Okay, where all of the, the 4 pi bits and stuff like that you get for the formula for the volume of a sphere get canceled out because I'm dividing two volumes. I'm dividing this sphere of radius d by this sphere of radius r. This should be r naught, by the way, r naught. Okay? So it's like the fraction of charge that's inside this little sphere. You see? Yeah. Okay. So these ZE's here will cancel, so we can get rid of those. I get E sub m is equal to ZE, that's the one that was left over. D cubed divided by d squared is just d over 4 pi epsilon naught r naught cubed. But ZED, that's just charge times this displaced distance, right? So that's the dipole moment. So that's equal to P over 4 pi epsilon naught r naught cubed. So I could write this as P equals 4 pi epsilon naught r naught cubed times E sub m. the molecular field. And recall that dipole moment is equal to alpha, the molecular polarizability, times the field, which means that alpha is equal to 4 pi epsilon naught times r naught cubed. Right, because here's P, here's P, here's an E sub m, and you see this must be that. Yes? You see that? Yeah. Just through the simple relationship here. So in your homework, I'm going to ask that you show, remember what I wrote before? Another version of the Clausius-Mossotti relation, right, is to write the molecular polarizability as 3 epsilon naught over n times kappa minus 1 divided by kappa plus 2, where kappa is the dielectric constant, right? I want you to show in your homework that this is the case. And so if I use this and substitute it in here, then what I can get, I'll say that this then is equal to this alpha. So this is equal to 4 pi epsilon naught r naught cubed. And you see that we can get the radius of an atom given its dielectric constant, right? So we can measure the dielectric constant in the laboratory, and now we can calculate from that what the radius of that atom would be. And I think I give you a problem in the homework that looks like that too. So it's going to be the cube root of, we'll have 3, the epsilon naughts will cancel, so I guess we'll have 3 over 4 pi n, right, times kappa minus 1 over kappa plus 2. Yeah, something like that. So we can use this formula, right? That will give you the radius of an atom, right? And this really only works for simple, monomers, like simple molecules that just have one atom, okay? But you can use it to do diatomics by basically just doubling the molecular polarizability. So if I want to think, what's the radius of hydrogen atom or helium or something, or not helium, but of hydrogen or nitrogen or oxygen, right? I could do oxygen, for example, right? O2. It's prevalent in the air. I could treat it as twice the molecular polarizability. I think that's the term. Treat it as twice the molecular polarizability to account for the 2 oxygen atoms, okay? So you can use it for simple things like diatomics and still manage to come up with something that's reasonable. And so I think I put a problem like that in your homework assignment to do, okay? Okay. All right, so let's see. We've considered, this is just for nonpolar molecules. So polar molecules, it's a bit trickier, okay? And that's what I'll go through next. And so let's have a look at that. Okay, so let's remember that the molecular field that we calculated before, which is quite general, I think we just called it E, so let's just plus P over, over 3 epsilon naught. Okay, and so my model, remember when we did the gas, we thought of modeling an atom as just like an electron and a proton separated with a spring? Well, we're going to model things a little bit differently this time. I want to think of ions as something like this, where this is a positive ion and this is a negative ion. So for example, sodium chloride, right? This would be the sodium, positively charged sodium atom and the negatively charged chlorine atom. But both of these, both the sodium ion and the chlorine ion, would have their own molecular polarizabilities. So associated with each one of these ions would be, I'll call it alpha plus and alpha minus. That's the molecular polarizability. But they'll be separated by some distance. We'll call this position x plus, we'll call this position x minus. And so this little delta x here is just x plus minus x minus. And since the dipole moment is equal to the molecular polarizability times the electric field, and similarly, it's also calculable as the charge times the separation distance, right? I can write a couple of terms here. So let me write Q, well, that's the charge associated with each of the ions. They're going to have the same charge, right? One will be positive, one will be negative. That way they all balance out, and it's not, it's electrically neutral. So we'll say Q times X plus alpha plus times E sub m, the molecular field. Both of these are equal to dipole moments, right? This one, I should have arranged it slightly differently, like this, right? You can think of the dipole moment as being a result of a charge times a displacement, or as a result of molecular polarizability times an electric field, okay? But we'll also have the negative Q minus plus alpha minus times the same molecular field, right? That's for the negative ion. If I add these two together, I end up getting Q times X plus minus plus alpha plus alpha minus times E sub m. You can see this is our dipole moment, and this is the dipole moment because of the molecular polarizabilities of the ions themselves. So I've taken into account not only the kind of the permanent dipole, because these ions are displaced, okay, and also the dipole moment that you get from the molecular polarizabilities of the ions themselves. Now, before, for the dipole moment per unit volume, we used this idea of a dipole density, like the number of dipoles per unit volume. We called it big N, right? But I'm going to consider something that's a solid now, okay? And this solid will be in a crystalline formation. And so I want to consider that dipole moment per unit volume to really be the inverse of a unit cell volume, okay? Because we're going to get one dipole per unit cell volume. And so I'm going to let the number of dipoles per unit volume go to just simply 1 over this volume. That's the volume of a unit cell, okay? And I may put a homework problem involving calculating a volume of a unit cell. I think it will. Barium titanate is a common dielectric crystal people are used to dealing with and working with. There's a lot of data out there on the internet about barium titanate. So I'll put some numbers in for that so that you can do some calculations on barium titanate, including calculating the molecular volume of the unit cell. So now, instead of writing that the dipole moment unit volume is N times the dipole moment, I want to write it as the dipole moment over this volume. Okay, or I'll put a vector on that because it usually is a vector quantity. So then I can write that this, if I divide each of these terms by this volume, then this will give me the dipole moment per unit. Dipole moment per volume, right? Big P. I guess you could call it the dipole moment density. I'm going to make a few changes here. I'm going to let X plus this term here, I'm just going to call this X bar, okay? And this term here, I'm just going to call this alpha with a bar over it, okay? So let me just write that off to the side here. I'll say that X bar is equal to X plus minus X minus divided by V, and alpha with a bar over it is equal to alpha plus alpha minus divided by the unit cell volume. So if I sub in for E sub m, this expression that we have up here from the first section that we talked about today, right, then I'll end up getting something like this. And see, I've got the dipole moment per unit volume on both sides here, right, which I'm just going to call polarizability. That's what I usually call it, polarizability. Polarizability on the right and polarizability on the left. So if I solve for this, what do I get? I get P equals Q times X divided by, plus alpha bar E sub m divided by 1 minus alpha bar over 3 epsilon naught. I'm going to write that over here because we're going to need this. Okay. So need some more room here. And so very similar to what we did with a simple gas molecule, I want to think of these ions as being separated with something that has a, I don't want to write K because we used something kappa for dielectric. This is just m omega naught squared, where omega naught is this kind of resonant frequency for the spring, right? It indicates how tight the spring is, right? How much it pulls back when you pull on it, right? It's a measure of its restoring power, right? So this spring we're going to think of as the thing keeping the two ions separated, but not separating too far apart. And we can write a very similar equation to what we did for the gas last time. I'll write mass times the acceleration, so omega naught squared times x, and this will be equal to the charge times E sub m, but we'll substitute in for E sub m. We'll get Q times E sub f plus Q times dipole moment over 3 epsilon naught. And just like last time, I'm not interested in acceleration. We're doing electrostatics here, right? So we're going to assume there's no acceleration. This will be a very interesting question for us perhaps later on down the line when we start thinking about moving charges, okay? This acceleration term. But for now, I just want to let this be 0 so that we're really only considering electrostatics, okay? And so what do we get? We get that omega naught squared. Also, I'm going to rewrite x, right, as x bar times the volume. right? Because remember that x bar was just equal to the x divided by the volume, and this will be equal to q e sub f plus p q over 3 epsilon naught. And then it's a simple matter to solve for x bar. X bar is going to be equal to q over m omega naught. I'm going to write it like this. Q over m v omega naught squared times e sub f plus p q over 3 epsilon naught m v omega naught squared. So just simply solve for x bar in this expression here. I can take this value and I can substitute it in right here in this term for the polarizability. See? X bar, replace this x bar with that. Q squared. Actually, let me write it like this. Think that is correct. Again, I want to solve for p here. So we can move this over here. That's going to end up giving me 1 minus alpha bar over 3 epsilon naught minus the q squared over 3 epsilon naught mv omega naught squared all times p, and that will be equal to this q squared e sub f over mv omega naught squared plus alpha bar e sub f. We're going to clean this up a little bit in just a second. I could factor out the e sub f here like this, and then we can make some substitutions here. I think we should let I'll use c equal to, I think I want this term here, q squared over m omega naught squared v. Q squared over mv omega naught squared. Q squared over mv omega naught squared. That'll take that here, so I can replace this with c. And this, q squared, I can see I can pull out this 3 epsilon naught out of this. Make that plus 1 over 3 epsilon naught times this. And this plus this, this plus this. Yeah, and so then I'm going to create a new substitution. Uppercase delta is going to be c plus alpha bar. So that I can replace this and make it a little simpler. I'm just simplifying things here, right? E sub f minus 1 over 3 epsilon naught times this. 1 minus. There we go. And so now we can write that P is equal to this delta over 1 minus delta over 3 epsilon naught, all, oops, not times P, times E sub F. It's a lot of really ugly algebra. I apologize for that. But if you make a few substitutions along the way, you can simplify things and write it a little bit neater. This is really actually the form that I want to get it into. You pull out an epsilon naught out of this, making this epsilon naught and putting an epsilon naught up here. That looks a little better. And so now I can compare this with P equals epsilon naught times kappa minus 1. This is just the relationship in general for the polarizability related to the dielectric constant, right, that we used several times before. And by comparing these two, right, I can see that kappa minus 1 in this case is equal to this delta over epsilon naught minus delta over 3. Okay? And that is kind of the result that I wanted to go for here, because this, if you look at this, right, it says something interesting is going on here, okay? And this is relevant for a certain type of material called ferroelectric materials. These are materials that maintain, that are the crystalline structures that maintain a permanent polarization. And what's interesting that happens here is you see if, as this delta approaches 3 epsilon naught, what happens here in the denominator of this guy? Right? If I replace delta with 3 epsilon naught, what do I get? I get epsilon naught minus epsilon naught. What's that equal to? 0. So this causes the dielectric constant to become gigantic, becomes huge. Okay? And so these ferroelectric crystals are usually characterized by really, really large dielectric constants. And this is the term that allows that to happen. Okay, if you look at what makes up this, right, we've got the the kind of the permanent dipole part and then the molecular polarizability part, right? Now these we know are typically on the order of 1 or rather small, but this term here can lead to, you know, these really large values that cause the dielectric constant to become very big, okay? And this is one of the consequences of, you know, permanent dipole moments, ferroelectric crystals, is that they have a very large dielectric constant. Now, it really depends on the symmetry of the crystal structure, right? Whether these kind of things are possible. And so there's a phase transition which takes place at a temperature called the Curie temperature, which distinguishes between these symmetrical crystal orientations where you do have a permanent dipole moment and those where you don't. And so in the homework there will be a problem involving barium titanate when it is below the Curie temperature, and so when it does have this permanent dipole moment, and you will do a calculation to see what that dipole moment per unit volume is, or the polarizability. And I think that's it. This was a kind of intense lecture. It's a lot of material. It can get very complicated. This is probably as much in the weeds as we're going to go, I think, in this course. But I hope it's helpful. And so that's it for now.